All right. I assume it's sharing. I did not know that this window could expand so much. I mean, how neat is that? So um, this little video is about vector components, which you've drawn. Oh, let's see. Well, we had the 4 dry ice scenarios, so there's 4 force diagrams, plus another 16 that were in the worksheet 1. So you've drawn 20 different force diagrams at this point. Every one of them has had the force of gravity in it. Can't get rid of it. So force of gravity in every one of them. And I'd kind of like to know something about this force of gravity, which is going to necessitate probably some kind of a lab. We're probably going to need to collect some data to find out some information about the force of gravity. We can't really do that right now because you're not here. So I'm going to not necessarily fast forward, but we need to do something specifically for what is going to be coming. We will do the gravity lab when you're back in person. But we need to do something about this vector stuff, because in those diagrams when we were doing those force diagrams and we were moving vectors around, like for instance, when we had these things going on and I was grabbing these vectors, it's probably gonna, oh good. So, and I'd move this one here and then this one here and then this one here. And so moving all these vectors around, that's great and all. And it's handy to be able to move things around tip to tail so that we can see how they would add. But mathematically, that doesn't really help. Like, I mean, obviously in these diagrams, we have no quantitative values. We have an arrow length and we have a direction. So vectors still have magnitude and direction, but we have no actual like numeric magnitude. And so if we want to quantify like how big, how much is this vector, how big are these forces with an actual number, we don't have the capacity to do that yet. We will, and that will be the next step. We need to do the gravity lab first, though, to kind of figure that out, how numerically things are going to work. But in the meantime, something that you will have to know once we have some values and some numbers, you're going to have to know this part. Now, this, folks, this is Algebra 2, I believe. I believe this is Algebra 2. We're talking trigonometry here, okay? So geometry / trig / Algebra 2. If you have a vector like this, like the orange thing here is a vector. If your vector is 15 units long, whatever that is, like I don't even have a unit of measure on it because we don't have that yet. This is just in general for vectors. How do you figure out? Well, let me say it this way. When that vector is at a 35-degree angle above the x-axis here, above the horizontal, that means that a certain portion of that 15 units is horizontal. There's a horizontal component, okay? And there's also a vertical component of that vector. That vector has, because it's off at an angle, some of it is horizontal, some of it is vertical. And so the question is, how much is each? And so this is a mathematical thing that you've already learned before, that you've probably, some of you long since forgotten. And maybe you weren't very good at it at the time you were doing this in math class anyway. And now I'm going to bring it all up again, and you're going to get hives and whatever. But we're talking about vector components, okay? It's all just a bunch of triangles. It's all a bunch of triangles. So here's what I'm talking about that you're gonna have to do. So I gotta click on the screen. Oh, whoa. Okay. So let's go with green here. There is a certain portion of this vector that is in the horizontal. Oh, I know what I should do. I should grab this. I'm going to lock in place. So there's a certain amount of this 15 unit vector that is in the horizontal, okay, which I've drawn in green. There is also a certain amount of that vector. Maybe I should call it, I'll call this vector, I'll give it a name. I'll call it A, I guess. We'll call it A. This vector's name is A. Vector name A. No, let's call it F. I apologize. Let's call it F because we're talking about forces. So we're going to just pretend it's a force. It's F. Okay. So that means a certain amount of F is in the horizontal plane here. Okay. Horizontal dimension. So I might call that Fx. That's the amount of the F vector, the value that's actually horizontal. And then there's also a vertical part. There's also a vertical part like this. Oh boy, that's not very straight. And so there's also a part of F that is in the, oh my gosh, that's in the Y plane or dimension. So we have two parts. We have the vector F, the 15 unit long vector F, can be broken apart into two pieces. Because it's at an angle, some of it is being pulled, some of it is in the horizontal, and some of it is in the vertical. And so how much is in each? How do you figure this out? In other words, what are the two legs of the triangle that we just made? So that's trig, okay? That's trigonometry. Some of you probably already know how to do this, and you're like, oh gosh, this is old news. Some of you maybe never really learned it, but had to do it and then didn't do well, or I don't know. So I'm going to show real quick like how this works, and then yeah, that's like step one here. So here's what we do. If I'm looking at, oh boy, if I'm looking at this angle here, and I know the hypotenuse, so I know the hypotenuse, and I have the 35-degree angle. If I just pick a trig function, if I just say sine of theta, which is the angle here, is the opposite over the hypotenuse. Opposite is the f sub y. Sine of theta is f sub y over the hypotenuse, or f. Y'all with me here? Opposite over hypotenuse is sine. So the sine of 35 degrees should be the opposite side over the hypotenuse. Opposite over hypotenuse. Which means sine of 35 degrees is the y component of this vector over 15, which is the length of the vector. That means Fy, force, the amount of force that's in the y, is 15 times the sine of 35, right? So is everybody seeing what I'm doing here? 15, that's supposed to be a 5. 15 times the sine of 35 degrees, which is, in this case, oh boy, let's see. I should use 30 degrees. It would have been easier. 15 times. Oh shoot. 15 times sine of 35 is 8.6. So 8.6 would be, that's the value, that's how tall this vertical component is. All right. Then we got the horizontal component. Well, if sine went with the vertical, then cosine here. So again, the cosine of this is talking about the adjacent over hypotenuse. So that means cos of theta is the adjacent, or fx, over the hypotenuse, which is just f. And so that means cos of 35 degrees is the x component over the 15, which is what f is. And so that means fx, the x component, is 15 times the cos of 35 degrees. And so the x component is, let's see what we got here, 15 times the cos of 35, which is 12.3, let's say, 12.29, 12.29. Now, positive, and that's positive as well. Now, why am I making a point of this? Because depending on which way the components are pointing, that could be different. So if your vector is down in the fourth quadrant here, then your y is going to be negative because it's down. It's in the fourth quadrant. Your x is going to be positive because it's to the right. Down here in the third quadrant, you're going to have a negative x and you're going to have a negative y. So you have to know which way the vectors are pointing on your xy coordinate system to know what your pluses and minuses will be on your components. Now, why do we have to do this? Because what happens if you have two vectors on the same grid here? This could be like a force diagram, right? Where there's two forces acting on it. What if you need to know the sum of these vectors? Like, what is the resultant? Well, if we're doing graphically like we did in our force diagrams, well, oh, are you kidding me? Is this all one piece? Okay. So if we're doing graphically, well, then you move it tip to tail, right? Move that down like that, tip to tail, and then you would draw a resultant vector. Let's see. You would draw a resultant, and then you'd say, oh, well, there it is. There's your resultant, the green vector. That's the end result of having the orange vector plus the blue vector. That gives you the green vector. That's your resultant. Well, that's great graphically, and we see the picture of that. But there are numbers here, right? There are values involved here for this to know how much those add up to. So, let me get that out of here. Let me put this back. So how do you add two vectors like this? Well, you do it by components. Okay. Now, I'm not going to mathematically figure all of this out. I'm just going to, using symbols. I probably shouldn't even have put numbers on this thing. But I'm going to show you how this would look. Okay. And these are called force summations. We're adding up all of the forces that are acting on the object. This is a vector summation. All right. So follow along. You probably should be putting this stuff in your notes, but so we have, for this vector, we have two parts. We have a vertical part, we have a horizontal part. So the vertical part goes down, and then we have a horizontal part that goes over, goes across. Now, if I'm going to call this one F1, then I might call the other one F2, just so they have a name. And again, notation is going to get messy, okay? Yeah, it's going to get messy. It's okay. I apologize. There's nothing I can do about that. Now, if I'm going to name them, then the components need a name as well. And so this would be F1x. This would be F1y. In other words, there is a portion of the F1 that's in the vertical, and there's a portion that's in the horizontal, and I didn't draw that very well. My goodness. Oh, the whole thing is, oh, seriously? Oh, well, it's good enough. And so we have an F1x and an F1y. There's two parts, okay? For F2, there are two parts. We have a vertical part, which we could call F2y. And then we have a horizontal part, which we would call F2x. F2x and F2y. So F2 can be broken down into two parts as well. Vertical part, horizontal part. Now, here's where things get a little tricky and a little messy, right? We have to add up the components. Like, how do you know what this vector plus this vector is? Well, you add the x's together, and then you add the y's together, and that gives you the resultant. That gives you the components to your new vector, like the green one here, okay? Like, since we showed graphically, the green vector is what you would get if you move tip to tail and add the vectors. Numerically, this is how we have to do this. You add the components. So this is what it's going to look like. We have the sum. That is a Greek letter sigma, capital sigma, Greek letter, which means sum, to add. That's why it's S. So the sum of the forces in the X. Oh, no. Oh, my gosh. No. The sum of all the forces in the X horizontal would be F1, oh gosh, X plus F2X. And what does that equal? The resultant. Fx, I won't call it F, I'll call it resultant. Rx, not prescription, resultant. Okay, that's the X component of your resultant vector, the green vector. And then you have to add the components in the Y, which means F1Y plus F2Y. And what does that give you? That gives you the resultant component in the Y. So that gives you the X component of your green vector, and that gives you the Y component of your green vector. And so from these two components, you can figure out, hey, how big is the green vector? How long is it? And what angle is it? Because you now have the components of your resultant vector. I hope this makes some sense. This is how you add vectors. You add vectors by component. You got to separate all the x's and all the y's, then you add the x's and you add the y's, and that is your resultant, the x and y parts of your resultant vectors. I hope that makes sense. So that's where we're headed. We're headed to this. So if you thought things were complicated earlier, oh my gosh, it's going to get worse. But it shouldn't be that bad. I mean, this is just adding vectors, okay? So I think that's all I need to tell you now. There is going to be a worksheet. I'm going to post a worksheet number 2. No, I won't. Just know that you need this information. You need to be able to break vectors down into their components. In fact, how about this? Here's your assignment. I want you to figure out what the F1y and F1x values are, and what are the F2x and F2y values. So again, I want the x and y components of F1 and F2. That's your assignment. All right. Find the x and y parts. In other words, this part and this part, this part and this part. Find these parts of these two vectors. Got that? That's all I got to do. Basically, it's this. You're doing this part right here, this part for this vector and this vector. And that's it. So I think I'm done. When you come back then on Monday, we'll talk about whatever, I don't know. This stuff. Gravity lab. We got to do the gravity lab. So anyway, hope you're doing well, and we'll see you soon. Take care.